So I welcome you to the afternoon session of today, and I'm very happy to announce Kiumars Kaveh from the University of Pittsburgh, and he is going to talk to us about vector-valued polynomial equations, toric vector bundles, and matroids. Thank you.
Yes, can you hear me well? Yeah, it's my absolute pleasure to speak here, and thanks to the organizer for inviting me. I'll try my best to give a good talk to get invited to IMPA again, to this renowned institute. I know IMPA from my back in undergrad at Shokrieh University. I was taking, as an undergrad, an advanced course in dynamical system graduate course, and I remember our professor was part of the course. He was translating some notes in Portuguese to Persian from some lecture notes from IMPA. But that's my first time here in Brazil and IMPA. It's an absolute pleasure for me. I'm also a fanatic fan of Brazilian football back from when I first time watched World Cup '82. So I'm pretty old. But I'm probably more fanatic about Brazilian football than some Brazilians. Okay, so I'll talk about relatively recent work. Yes, the paper. The paper will be in archive. Hopefully, the preprint. Hopefully, in a couple of weeks. In a few weeks. And most of the delay is my fault. And it's about some far extension of Newton polyhedra theory and theory of which can be thought of as theory of line bundles over toric varieties in fancier algebraic geometry language. And this, what I'm talking about, is related to, and if there is time, I'll briefly mention the connection with torus equivariant vector bundles and toric varieties. But for people who do not come from toric geometry, don't worry. I'll mostly talk about at least the statement and definitions are very basic and can be understood with linear algebra and high school background. Of course, you have to know complex numbers. I'll work for over complex numbers, but the choice of base field is not important, and any algebraically closed field should be fine. Maybe to be safe, I'll assume characteristic 0, but I'll work over complex numbers. This is joint work with Askol Chovansky, my PhD advisor, and one of the main players in toric geometry and inventor of basically Newton polyhedra theory, and Hunter Spink. And these are pictures of my co-author. This is Askol, this is Hunter, if you can tell. So Newton polyhedra, maybe a quick recap of or review of the Newton polyhedra theory. So the name Newton refers to notion of Newton polygon that Newton introduced in a letter to some guy, and it's basically Newton is basically introducing a non-Archimedean version of Newton method, which we learn in calculus, and and then Newton polygon is related to that. It's solving f of x, y equal to 0. F is a polynomial, and then you want to solve y as a series in terms of x. You cannot have integer exponents. You may need to have fractional exponents, and then using this convex geometry trick, Newton can say what is the leading exponent of y as a series. Anyhow, that's a local theory, and I think in the 70s, Vladimir Arnold suggested to his students and his school, some of his students, including Askol Chovansky, to work on global versions of Newton's theory, and that's what resulted in Newton polyhedra theory, and then which is a global theory. At least what I'm talking about is a global theory. So the basic definition is very simple. So you have a polynomial, Laurent polynomial, So my notation is that x stands for x1, xn, n tuple of complex numbers. X to the alpha is shorthand for a monomial with exponents a1, an. I write x to the alpha, a character of torus. C star to the n or C cross to the n, we call it algebraic torus, just setting, and I usually denote it by T. And this is a ring of Laurent polynomials in n variables. I write it Cx plus minus. And then Laurent polynomial, I denote write on a sum of C alpha, X alpha. X alpha is a monomial, C alpha is a complex number coefficient. And the main, and then the Newton polytope of delta or Newt f or delta f, I usually like to write delta f is convex hull of the exponents that appear with non-zero coefficient, and it's some polytope in Rn with lattice or integer vertices, obviously. And then if you fix a set of monomials A, I write denoted by A or fancy A, fix a set of monomials or exponents, we can define a subset L sub A of or Laurent polynomials which have these monomials, given monomials, and then the coefficients are arbitrary. It's of course a finite dimensional subspace of Laurent polynomials. It is exactly such subspaces of Laurent polynomials are exactly torus invariant subspaces of C of T or Laurent polynomials. This is infinite dimensional vector space. T acts on it, and invariant subspaces are exactly of this form. A is the set of weights of the invariant subspace. Okay, so these subspaces are one-to-one correspondence with T invariant subspaces. And let me take delta to be the convex hull of A, which is a Newton polytope of a generic element of my subspace. Okay, some very basic material. I hope everybody's okay with that. I hope if I'm going too slow, please feel free to take a nap. If I'm too fast, please stop me. And so the problem is that, the main problem is that, first my notation for this, if I have R Laurent polynomials, I denote by the zeros, common zeros of this system in torus, not in affine space but in torus, of course, by Z of F1, Fr. And then I'm taking R to be number of equations to be less than or equal to number of variables. And then, so the problem is that you fix a bunch of sets of monomials A1 to AR, and then you pick a polynomial with given Fi, a polynomial, Laurent polynomial with given monomials. So Fi is coming from La sub I, and then you look at the Z of F1, Fr, and then you want to understand some invariance, topological or geometric invariance of this subvariety, which we can call it a complete intersection because it's given by as many equations as the codimension. But the catch is that we want Fi's to be generic. So from our topological arguments, it's not hard to see that, or usual algebraic geometry arguments, that invariants of this subvariety are the same for generic choice of Fi's. Okay. And generic means if this is a finite dimensional vector space, so generic means in a Zariski dense, non-empty Zariski open set. And then the first theorem, which is if R number of equations is equal to number of variables, you have n equations, n unknowns. So you have generically you have a finite set of points. That finite set of points only depends on the choice of A1, An, not on the choice of coefficients, generic coefficients for the polynomials. And so the question is how many points are in this finite set? So or how many solutions the generic system has. And then famously, Kuchnirenko found this theorem in the case that all the equations have the same Newton polytope. Bernstein and Chovansky extended it to arbitrary systems, not with the same Newton polytope. And then, so number of solutions is n factorial volume of the Newton polytope when they have same Newton polytope. Then if they have different Newton polytopes, or A1, AN don't have same convex hull, it is n factorial mixed volume of the corresponding polytopes. Delta I is convex hull of AI, the finite set at AI. Should I quickly recall what mixed volume of polytopes? Mixed volume is a volume a function on the space of polytopes together with Minkowski sum and a scaling by positive scalars is a polynomial. This is a theorem of Minkowski, is a polynomial of homogeneous polynomial of degree n, and then any homogeneous polynomial on a vector space comes from an n of degree n. Any homogeneous polynomial of degree n on a vector space comes from a n-linear function, unique n-linear function, which on the diagonal specializes to the homogeneous polynomial. And if you do that linear algebra construction to volume polynomial, you get what is a mixed volume. So with respect to Minkowski sum of polytopes, this is n-linear it is linear in each component. Okay. And then Chovansky extended that theorem also to basically that theory to other questions and find computing. So now number of equations is less than or equal to n. So you may number of equations is r. So you may have not have finite number of points, but just a subvariety of codimension r defined by r many generic equations. And then out of the polytopes, he gives formula for geometric genus, arithmetic genus, topological Euler characteristic, mixed Hodge structure, etc., etc. I think in his famous work on mirror symmetry for toric varieties, Viktor Batirev used his computation of Hodge, mixed Hodge structure, etc. And one other comment is that if f's are not generic, so in this, back in the BKK theorem, I refer to this theorem, Bernstein-Korchinenko-Chovansky, as BKK theorem. In BKK theorem, which you have a finite number of solutions, number of equations is equal to number of variables. As I said, if you pick generic equations, you have a number of solutions is given by the mixed volume. If you don't have generic equations, then number of solutions is less than or equal to that number, the mixed volume, and factorial mixed volume, which is usually called BKK bound. And the reason is that if you think of a toric compactification of torus, basically some solutions may lie at infinity. So first of all, some solutions may be degenerate and they have multiplicity, so it reduces number of them. Also, some solutions may be at infinity. If you are in a generic situation, there are no solutions at infinity. All solutions are simple, and you have exactly that bound. But But also, you can effectively compute genericity. That's also for computational purposes is important. You can, given a bunch of equations with given Newton polytopes, you can effectively by some derivative computations, then that goes back to Chovansky, work out whether L is generic, and so the number of solutions, Fi's, are generic, or number of solutions is equal to the bound or not. So generic is verifiable and can be defined. It's not just for some choice of f's you have the bound. Okay, and another example of the Chovansky's theorem is that if you have one equation f of f equal to 0, you have a hypersurface, then what is the geometric genus of your hypersurface? Is number of lattice points in the interior of the Newton polytope. and it generalizes the well-known formula for genus of a curve of degree d. Okay, as I mentioned briefly, the fancy version of this story is that you have a toric variety corresponding to it, and then a bunch of polytopes with normal to the fan. Each one defines a ample bundle on the toric variety, and then you basically are looking at a subvariety defined by sections of the line bundle, these line bundles, which is a complete intersection, generic sections of your line bundle. And then if it's also familiar for people for people who know toric varieties, that if you have a line bundle associated to a polytope, and then you look at the lattice points inside the polytope, I call it A. This subspace L sub A, which is Laurent polynomials with exponents or monomials from A, basically are a basis or correspond to a natural basis for the space of global sections. So this is what is the relation between toric varieties and this Newton polyhedral theory. But in that, the previous setup, A is arbitrary set of points, does not need to be all lattice points inside the polytope or all lattice points in the Newton polytope. Any questions so far? Okay. Okay. Now I want to extend this setup to vector-valued Laurent polynomials. What do I mean by that? Instead of coefficients to be a scalar, coefficients of a monomial, coefficients of monomials to be a scalars, I want them to be vectors. Vectors from a vector space which I call E. In matroid theory, E is usually ground set of a matroid. Sorry for, I hope I'm not confusing people who are expert. We have experts in matroid theory here. So for me, E is a R-dimensional vector space. R is separate, completely independent from the torus, which is n-dimensional, but dimension of E is less than or equal to n. Okay, and then the data I'm given is the following. As before, I'm given a set of finite set of monomials, finite set of lattice points, which each one I think of a monomial. And then for each alpha in A, I'm given a subspace in my vector space E. I have a subspace E alpha in vector space E. It's given, it's a non-zero subspace. It's given but arbitrary. So there is no restriction on choice of these E alphas. So just some arbitrary arrangement of subspaces. So you have an arrangement of subspaces in E. Each subspace of any dimension you wish, just non-zero. Each subspace is labeled by a lattice point or a character of the torus or a monomial. Okay, so that is the given data. And then I look at Laurent polynomials, which I can represent it in this tensor product. This is usual Laurent polynomials. I tensor it with E. I think of these are just morphisms from T to E, from torus to E, regular maps from torus to R-dimensional vector space. You can think of it like this. And so these are Laurent polynomials whose coefficients you can think of are coming from E. But what restriction I have on the Laurent polynomials? The coefficient of x alpha comes from the attached subspace. Okay, so I look at such Laurent polynomials that the coefficient of x alpha comes from the subspace attached to it, and then this is a finite dimensional subspace of a space of vector-valued Laurent polynomials. I can say. And in an obvious manner, these subspaces which decompose like that are basically invariant subspaces of the tensor product, where torus acts only on the second factor. Okay, and then you can repeat the previous definitions and then say consider f of for some f vector valued Laurent polynomial, you can ask for, it defines a subvariety in the torus. Basically, f equal to 0 amounts to r many equations, and if f is chosen generically, then you have a codimension r subvariety, but this can be thought of as section of a vector bundle. So in general, it is not a complete intersection, and in this sense, this equation or this kind of subvariety is
found this on the web.
Shut up. Far generalize the previous question of having r many separate equations where coefficients, each equation had fixed Newton polytope, and then the coefficients vary independently. Here, the coefficients, if you think of it as a system of r polynomial equations, r is the dimension of E. The coefficients are very dependent. It very, very much depends on the arrangement of subspaces I started with. Okay, so it's does not reduce to the previous problem, and it's much more. In general, it's much more. Situation is more complicated, of course, depending on what questions you are asking. But and then the goal is that I extend BKK theorem to this setup.
The E alphas are subspace in the sense they pass through the origin, or?
Yeah, vector subspaces. Yes, vector
And
subspaces.
that's important, or
We want to have a subspace, vector subspace of functions. So you again, I would say.
the system of equation would be more general if you allow.
Yeah, a scaling of the equations, because I think I would say it is important that I have vector spaces. Yeah. Okay. And again, fancy version is sections of a vector bundle over a toric variety, which is a vector bundle is called a toric vector bundle, means that it is equipped with linear action of torus. Okay. And then if you want to think of matroids,
The previous week.
sorry.
I mean, at the start you put r smaller than n, but you are finally interested in these zero sets, right?
Yes.
Which are divided by many conditions. Maybe, yeah.
This year, yes. So if you have more, r is less than or equal to n because you want to have less equations than unknowns. So if you have more equations are bigger than n, it may be empty, may not be empty. You can allow that and then ask other questions. For example, you can ask for under what condition it's empty, not. And we also have some. Khovansky has, in the case of in the previous setup, has theorems about when a complete intersection is empty or not in terms of Newton polytopes, and similar answers should work in that case too. Yeah. So yes, you can allow for r bigger than n and ask other questions.
I would rather say that, I mean, for non-emptiness, it's rather the sum of the dimension of these spaces.
Yes. Okay. And yes, Matroid setup is that you pick a finite set of vectors. These are normal vectors to the hyperplane arrangement Kris was talking about. So you have a finite set of vectors in a vector space, and to each element in your matroid, in your matroid, you can assign a finite set of characters or a polytope pi, and then you can take functions, Laurent polynomials, who are linear combinations of your vectors times a Laurent polynomial with given Newton polytope, as I have written there. It's an equivalent setup. But this setup would extend. You can ask, as I'll mention, this will be related. You can ask some questions about when this M is not representable matroid. What is that? Decided to play some music. Okay. Okay, so now coming to the main results. Sorry for the long introduction and setup. Okay, so to L, we assign a sequence of polytopes which encodes the combinator. The first has the need. It's about convex geometry and the characters, the sets A of characters we pick, and also about the combinatorics of the arrangement of subspaces we have. And this sequence of polytopes, we call it characteristic sequence of polytopes, they actually are directly related to chain roots of covariant chain roots of a vector bundle which is behind the scenes. And by definition of this delta I, the deltas are very combinatorial and straightforward. So you pick a bunch of I tuple of, I'm defining delta I. Ith polytope in the sequence. I look at an I tuple of characters, maybe with repetition, doesn't matter. So alpha 1 to alpha I is I of the characters. And then I take alpha 1 plus alpha I if in the corresponding subspaces I can find the vectors which are linearly independent. Okay, and I pick all such sums, and then I sums of I fold sums, and take convex hull of them. So it has the combinatorial data of this arrangement or matroid data and the sum of the characters. Okay, so we get these polytopes, and the main first theorem is that if R is equal to n, which means number of the rank of the vector space is the same as the number of variables or dimension of the torus. The number of solutions of our system, vector valued equation, number of solutions of a vector valued equation is given by n factorial, some n factorial mixed volume. But the mixed volume is mixed volume of differences of these polytopes. How should I interpret that difference? In convex geometry, sometimes they call difference, formal difference of two polytopes, they call it virtual polytope. Maybe I can write something on the board. So you have notion of Minkowski sum of polytopes, and it's a cancellative operation. So you can formally extend it to a group or a vector space by introducing formal difference. The same way out of integers you construct with multiplication, you introduce formal quotient of integers, which are rational functions, or field of fractions. This is formal difference of polytopes, and which becomes a vector space. Or another way of thinking about that formula is by multilinearity, expand that expression, and you get a alternating sum of lot of mixed volumes of the delta i's. Okay, so these are so you get mixed volume of delta 1, then delta 2 minus delta 1, delta 3 minus delta 2, and so on. So that mixed volume times n factorial exactly gives the number of solutions. If R is less than or equal to n, we get a subvariety inside torus not just a finite number of points, you get a subvariety inside torus. And there is something called the ring of conditions of torus, which is basically the place to do intersection theory for subvarieties of torus. Another way of thinking of ring of conditions is the limit of all cohomology rings or Chow rings of all toric compactifications of torus. And each subvariety in torus defines a class in that ring, basically limit of all Chow rings. And it has a combinatorial description by weighted fans, which Kris this morning mentioned. And we get this description of the class of my subvariety inside ring of conditions as product of classes of these virtual polytopes. For people who are not that familiar with this story of ring of conditions, intersection, tropical intersection theory, and so on, you can skip that. But there is a combinatorial description of this class of this variety, intersection theory class of this variety. This is little bit different formula for out of this you can compute the weighted fan of the subvariety, but it's given in a little bit different way, a style, as product of classes of polytopes or virtual polytopes. Yes?
You say the mixed volume of the virtual polytopes can be expressed in terms of mixed volume of actual polytopes?
You just, that expression, you have minus signs. Just by linearity expand it. Just open the brackets and you get some expression with lot of plus or minuses of mixed volumes of delta i's.
And that formula can be interpreted nicely?
No, I mean, I'm just saying something obvious.
No, I think I realize what you
Yes.
said. That's a different looking formula. Can you say what those signs coming from combinatorially? Does it have an interpretation after you expand it?
No, not here. But yes, that does. I don't think it has any interpretation, useful interpretation that I can think of. Okay. And then a small comment is that if in this previous in this setup, if the subspaces if the subspaces I'm taking are coordinate subspaces with respect to some basis for E, for example, a standard basis for my vector space, then this recovers the setup in the BKK theorem. But if you have just some complicated arrangement of subspaces, it's different. And then you can ask a example of also this situation is the following, which is also Kris for us basically defined a lot of the things this morning. So you have an arrangement of subspaces. My setup is that I'm in CPN or PN. Kris denoted it by D. D was dimension, and my little n is the dimension. Okay. So I have an arrangement of subspaces defined by some linear equations ui equal to 0, and the projective space minus the arrangement is that L, which Kris was talking about this morning. It's a linear space minus minus some intersection of a linear space with the torus, and this exactly fits in the previous more general setup, and you can answer this. You can compute what these delta i's are. They are the convexal of these sums of a standard basis elements. So this is the ej1 plus eji is the vector that has in these positions has 1 and then other positions has 0. So such kind of vectors. But for what choices of j1 to ji where the corresponding hyperplane arrangement, hyperplanes intersect empty, intersection is empty, but not for not over J1 Ji, but in the complement of this set. So if you want basically for matroid, from point of view of matroid theory, you are looking at a dual matroid. Anyhow, so there is some combinatorial polytopes one can explicitly define, and in this case from the intersection of combinatorics of intersections of this hyperplane arrangement, and then it answers as a special case of the previous theorem. It says if you have, it's more general than BKK theorem, so you have polynomials F1, Laurent polynomials F1, Fn with given Newton polytopes, but instead of variables from torus, you are putting, instead of u, x1, xn, I'm putting some fixed linear combinations or linear forms in my variables. So it's a BKK theorem, but with a linear change of variables, which is like completely more general than the usual BKK theorem. And then the answer then is given by some mixed volume. The number of solutions of such system is given by a mixed volume, which you have to put, this is consecutive differences of my polytopes, characteristic polytopes, and then the Newton polytopes of the equations. So it's given by such a thing. And just by looking at that expression, it's not even clear that this mixed volume is positive, but it is positive because number of solutions is a positive number. Okay. I'm writing everything in homogeneous coordinates, so the Laurent polynomials I'm taking of degree 0. It's usual, very usual thing to do. Any questions? So these are Laurent polynomials instead of each variable, I have a fixed linear form of other variables which I call x. Okay, so coefficients of fi's are generic, but u0, un, my linear forms are fixed. They are not generic. They are fixed. Okay, and then finally we get to Alexandrov-Fenchel inequality, which has played an important role in geometry analysis, and recently by work of Junha and collaborators, very important role in combinatorics and proving a lot of conjectures in combinatorics, etc. For people who have not seen this inequality, which involves mixed volume of polytopes or convex bodies, it's a reverse Cauchy-Schwarz inequality for mixed volume. So from kindergarten, if you remember, Cauchy-Schwarz inequality is this. But if you fix, if you have a n-dimensional polytopes, a mixed volume has n components or n inputs, and then you fix n minus 2 of the inputs. So p1, pn minus 2 are fixed polytopes. And then p and then you have a, if you fix the n minus 2 first inputs of mixed volume, then you have 2 inputs left, and then it becomes a bilinear form in the last 2 components, PQ. And then basically Alexandrov-Fenchel inequality says that this bilinear form satisfies reverse Cauchy-Schwarz inequality. Okay, and in fact the signature is -1, -1, and 1. That's bilinear form. And Khovansky and Tessier independently observed many years ago. By now, it's a classical theorem, classical theorem, that this intersection numbers of subvarieties in an irreducible variety, also intersection numbers of subvarieties satisfy similar. Intersection numbers of divisors or hypersurfaces satisfy a similar inequality. By applying Khovansky-Tessier to our setup, one basically gets that you get that mixed volume of, if you put the characteristic polytopes for an rank n-2 subspace, the consecutive differences of them in the mixed volume formula, and then the last two are free, so you get a bilinear form on the space of polytopes. That satisfies Alexandrov-Fenchel inequality. It is an extension of usual Alexandrov-Fenchel inequality, because Alexandrov-Fenchel, it's absolutely important that here you have polytopes, and for fancy algebraic geometers, they correspond to ample or Neff or ample divisors. So you have to have some positivity, which in our case means they are polytopes, not virtual polytopes, but actual polytopes. But here, these are not. These are virtual polytopes. They are not single polytopes. They are differences of polytopes. Nevertheless, we still have a Alexandrov-Fenchel inequality or reverse Cauchy-Schwarz inequality. And finally, before I move on to non-representable matroids, any question about this Alexandrov-Fenchel inequality? Yes?
So in algebra geometric terms, what should I think about? You're going to vector bundles, but you still have some positivity?
Yes, the positivity is that if you think about the the positivity is that even though this class, if you think of this as a class in the ring of conditions, this class is represented by an actual irreducible subvariety. It is not formal difference of subvarieties. It is one subvariety. But because it comes from a vector bundle, it is not represented by product of polytopes, classes of polytopes. It's different product of classes of virtual polytopes. But still, it's positive in the sense that it is represented by one subvariety. And that's why you can apply Khovansky-Tessier to that subvariety. Yes? Yes, sir, Oliver.
Similar question. If you would replace the delta i's as this formula by any polytopes, this would be wrong? Or
Sorry, if you...
I mean, this difference are
yes, it would be very wrong. Yes. Thank you. Thank you for the question. Yes, so these are very special polytopes. So if you have just arbitrary sequence of polytopes and then take the formal differences, it's wrong. This equality would be wrong. Yes?
So what do you know about which sequences of polytopes can arise as sequence of characteristic polytopes?
We don't know. We like to know. And we have, I would say we soon will start focusing more to understand and connection with other inequalities, Alexandrov-Fenchel inequalities in the context of matroids and Dusty Ross's normal complexes, and he has an Alexandrov-Fenchel inequality for those. It may have to do with that stuff, but the ideally one would like to have some, as you asked, to have some description or at least some large class of polytopes for which this inequality holds, but we don't know yet. Thank you. And then if you look at the definition of the polytopes, those characteristic polytopes, it's word by word works for any matroid. So instead of an arrangement of subspaces, you can just have arrangement of subsets of a matroid. A matroid, I mean a finite matroid. And and Matroid notion of dependence, independence makes sense. So word by word, it works for any Matroid. Just there is no, if you work with an abstract Matroid and not a representable Matroid, non-representable Matroid, then you don't have a system of equations or a vector valued equation, but you have the sequence of polytopes. And then you can write down you can ask whether it satisfies Alexandrov-Fenchel, and it does. And the proof uses the big theorems of log concavity or Alexandrov-Fenchel that June and collaborators proved. So we basically can reduce this question to their results. I would say the reduction is non-trivial, but also not super complicated to the known results of June and others. And so these polytopes coming from a given matroid of rank R satisfy Alexandrov-Fenchel inequality, where I'm taking rank to be n minus 2. So you have n minus 2 polytopes, and the last 2 polytopes. Then if you sub it in the mixed volume, you have a bilinear form. Okay, and okay, I have a few minutes. Yeah, so this is maybe I can say a few words about multi-valued piecewise linear functions. In convex geometry and toric geometry, is well known that for each polytope you can assign a piecewise linear function, which is called support function of the polytopes. You can extend this correspondence to virtual polytopes, and more generally to sums of polytopes, in the sense that which Chovansky, this is basically about polytope algebra, which was also mentioned in previous talks, but in point of view of Chovansky and then theory of Chovansky-Puchlikov theory, you call a convex chain, which is, I think, would be an element of the polytope algebra, a finite combination of a linear combination of characteristic or indicator functions of polytopes. So instead of just one polytope, you have several polytopes. You sum up their characteristic functions with some integer coefficients. So you get a step function. And turns out that these polytopes, these convex chains, finite sums of finite linear combinations of characteristic functions of polytopes, have also a notion of support function, but instead of one valued support function, you have to have a multi-valued support function. So you take support function of your polytopes, pi, h of pi are support function of the polytopes that you take their linear combination, and you think of it as it's not a sum of values, it's a sum in the group algebra, meaning that you have this value and repeated this many times. But you also can allow for repetition to be a negative number. So you think of it as a multi-valued function. And there are some non-trivial statements here that such a function, a convex chain, can be broken up into linear combinations of polytopes in different ways. But this multi-valued function is independent of the way you break the convex chain or represent it as a sum of characteristic functions of polytopes. And you can define a mixed volume. You can define a mixed volume for an n-valued support function by using the mixed volume of polytopes. I skipped that, and then it is well defined. And to basically to our setup and then invariant subspaces of vector valued polynomials, you can assign, or subspace arrangement labeled by characters, you can assign a multi-valued support function. And this support function is basically responsible, multi-valued support function is responsible for all the computations or all the answers to the computations. And those characteristic polytopes are one way of representing this multi-valued support function. There might be different ways to represent it as a sum of polytopes or sum or difference of polytopes, but all the answers agree. And finally, I think I'm out of time. I just want to say that this multi-values, for people who are familiar with theory of toric vector bundles and their characteristic classes, these multi-valued support function is basically encoding the, in this setup, basically encoding the chain roots of a toric vector, equivariant chain roots of a toric vector bundle. If you are interested to hear more about that side, I can tell you later. Okay. I think I'll stop here. Thank you very much.